Hey, how you guys doing today? This is Colin, also known as CYIT on YouTube. And today we'll be working on the first video of our Arithmetic Logic Unit for our mid-meter 8-bit computer. So here's what our Arithmetic Logic Unit looks like. It's right here in the middle. And on the left side, well, I know that the camera's at the top, but on the left side, it'll be our B register here, and then this will be our A register. So if we just kind of specifically take a look at our Arithmetic Logic Unit, what we have is a 74 LS245. We have that on both of our A and B registers as well, so we should know what that is. It's an output buffer, and it allows us to enable when we want to and decide if we want to send the output from our Arithmetic Logic Unit to our bus. We also have two 4-bit adders. And then lastly, we have an exclusive OR, well, two exclusive OR gates. In one of these 4-bit adders, we have a single half adder, and we have 3 full adders. So let's kind of talk about what a half adder is, right? So all a half adder is this is exclusive OR gate here, and we also have an AND gate that takes those same inputs from our exclusive OR gate. So what'll happen is, let's just use this example. So here we have a 1 and a 0. We have a 1 and a 0 here on our A and our B. And the way the exclusive OR gate works is if you have an odd number of inputs, so a 1 and a 0 will be an odd number of inputs because we only have one 1 that's going into our exclusive OR gate, then we'll get a 1 out. And if we have an even number of inputs, whether it be 0, 0 or 1, 1, then we'll get a 0 out. So like I said, we have a 1 here, we have a 0 here, and a 1 and a 0 will give us a 1 out for our sum input. So that'll be here. And then our carry input here is connected to our AND gate. We'll get that from our AND gate. And as you know, well, as we all know, we need 2 1s to get an output from our AND gate. So that's going to be a 0. So we have a 0 for our carry and a 1 for our sum. If we get a 1 and a 1, we'll have 2 1s go in. That's going to give us a 0 from our exclusive OR gate. We'll get a 1 and a 1 from our AND gate, and we'll get a 1 for our carry out. So we'll have a 1 and a 0, and then a 0 and a 0 is straightforward. We'll have a 0 for our sum, and we'll have a 0 for our carry. So 0 and 0. Now, a half adder and a full adder are similar, but a full adder has a little bit of extra logic to handle a carry input. So some of you may not know what a carry input is, and I'm here to tell you. So say we have 19 plus 14. So this isn't necessarily binary numbers, but this is a good way to view it. We have 19 plus 14. And we all know, we just want to add it. 9 plus 4 will give us 13. So let's go ahead and write that really quickly. So because 9 plus 4 is 13, we'll put a 3 here. We'll put a 1 here. This additional 1 is considered to be a carry. So this will be a carry input from, say, our half adder to our full adder. So our half adder isn't able to calculate 3 numbers at a time, but a full adder is. So that's why we have a single half adder, because that first half adder does not need to account for a carry input because it's the first one. And then we have 3 full adders because they will have to account for a carry input. And, if we did finish adding this, which we don't really have to, it'll be 33. So next we have 2 exclusive OR gates. And what we're using our exclusive OR gates for is to invert. So, hey, somebody may ask me, how do we invert using the exclusive OR gate? Why didn't we just use a regular inverter? So this is how inverting with an exclusive OR gate works. And this is right next to our 19 plus 14 example. But don't worry about that. So say we have our 2 exclusive OR gates, and at one we have a 0, and at another one we have a 1. So this is how the inverting works. Like I said earlier, an exclusive OR gate only works if the number of true inputs is odd. So let's say we add a 1 on our subtraction signal here, which is this line connected to the other input of our XOR gates. So a 1 and a 0 is an odd number of inputs, true inputs. So we'll get a 1 out. And a 1 and a 1 is an even number of true inputs. So we'll get a 0 out. So if we had 8 of these on this line and we added a 1, as you can see, it would invert every single output. So you may ask, why do we need to invert our outputs? Why would we need to invert our outputs? So our two 4-bit adders, they're used for calculating addition, obviously, but we may want to subtract as well. You know, we may have something where we want to subtract values. And you could still ask, okay, cool. Well, we may want to subtract values, but what does that have to do with us running our B inputs through our inverter first? Well, it's because of something called 2's complement. And what we use 2's complement for is to get the negative of a binary number. So say, for example, we have 2, which I'm not going to put in there right now, maybe a little later, but we have 2 inside of our B register, and that B register is going to go to our exclusive OR gate, and it's going to go to our AND gate. So number one, we didn't just use regular inverters because we don't want to invert all the time. We only want to invert when our signal, we only want to invert when we want to subtract, but sometimes we may want to add. So that's why we use inverters, first of all. That's why we used exclusive OR gates as opposed to inverters, right? But going back into what 2's complement is, 2's complement gives us the negative of a binary number. So how does this work? So first thing you want to do is you want to invert every single binary digit. If we have 8 bits and we have a 1 0 1 0 1 0 1 0, we want to have 8 bits and we want to have 0 1 0 1 0 1 0 1. So that's what we're taking care of right here with these exclusive OR gates. Not only do we want to, invert every bit, we also want to add 1, right? So let's see how we can do that. So here is a schematic of how this works. And it's pretty straightforward, but I'll explain this bottom part. So like I said, we have our B register coming in, and first is going through our exclusive OR gates. And then we also have that connected to our subtract signal. And when that goes high, it'll invert every output of our B register. But not only is it inverting every output of our B register, it's also sending a 1 into our adders. You see what I'm saying? So that's how we'll take care of our inverting, as well as that adding 1 to handle, for 2's complement. And then let me show you guys an example of 2's complement, because maybe it'll be a little easier to understand, right? So here, 8-bit binary number, 0 0 1 1 0 1 0 1. And we have 1 at 32, we have 1 at 16, we have 1 at 4, we have 1 at 1. So 32 plus 16 plus 4 plus 1 is 53, right? Okay, cool. So next, what we want to do, like I said, is we want to invert every binary. We want to invert every bit. So instead of 0 0 1 1 0 1 0 1, we have 1 1 0 0 1 0 1 0, and that's going to give us negative 54. Once you add it all up, right? So that's going to give us 1 less than what we want, which is negative 53, because we want to find the negative of this. So okay, cool. Now we just want to add 1, and once we add all of that stuff up, negative 128 plus 64 plus 8 plus 2 plus 1 plus that additional 1 here, we'll get a negative 53. So that's how 2's complement works. So if we had a 53 and we wanted to add our 50, if we wanted to subtract our 53, we'll turn our 53 into a negative 53 and then add whatever's in the A register with our negative 53, and we'll get our output, right? That's pretty straightforward. So now that we've got all of our theory out of the way, let's get right into testing our arithmetic logic unit, right? So here's the deal. Our first step is to connect our power, like so. So we connected it to power, and for testing, what I want to do is I want to go ahead and add 2 into both our A and our B register. So let's get that done really quickly. So 1 clock pulse, that didn't work. 1 clock pulse, we have a 1 here. We're going to load on our B register, 1 clock pulse, and we also have a 1 here, or I'm sorry, a 2 here. So what we have is a 2 and a 2, and a 2 and a 2 gives us a 4, as you can see. So that's how we know it's working, exactly how it's supposed to be working. And we can press our button again. And as you can see, what happened is we got the value that was stored in our arithmetic logic unit that went to the bus that was being pulled into our A register to go here. So we got 4. And then we still have that +2 on our B register, and a 4 plus 2 will give us a 6. So what's going to happen next is the 6 that is on our B register, our bus is going to go to our A register, and then it's going to, the arithmetic logic unit is going to count or add up that 6 plus that 2, and it should be an 8. Nice. And then we'll go ahead and get 10. And then, 12 what happened, and 14, and all of that good stuff, and so on and so on and so on. So now that that's happened, what I want to do is I want to talk about subtraction. And so let's talk about subtraction. So here, as you can see, we have a 12 here, and we have a 2 here, and 12 plus 2 will give us 14, as you can see. And if we go to subtract, 12 minus 2 should give us 10. So we have a 8 and a 2, we have a 10 here. So 12 minus 2 is 10. Let's press that button again. We should get an 8, which is nice. And then we'll get a 6. Perfect. And then we'll get just a 4. Nice. And then we'll get a 2. And then we'll go ahead and get 0. Perfect. So that's working perfectly fine. We're adding, we're subtracting. Everything is working how it's supposed to. So now that we're at 0, what we can kind of talk about is negative numbers. So number one, the sign bit will be our most significant bit. And all it does is it indicates a negative number, right? So here we have 8 bits, which means our most significant bit will be right here, our leftmost bit. And if our leftmost bit is at any point, if it powers on, then we know that our outcome is going to be negative. So let's see what happens when we press our clock module button one more time. All right, so what we get here is we get a 0 in our A register, and we get a 2 in our B register, right? So like I said, again, most significant bit is on. So we know we have a negative number, and 8 bits, the highest it goes up to is 128. So what does that mean? It means that because this is on, this value, as opposed to being 128 right here, is going to be a negative 128. And like I said, it'll be 0 minus 2. So if we just went ahead and added that up, take out my handy dandy really quickly. So we have negative 128 already, but all of these, every single one of these values to the right is still going to be positive. So what does that mean? Okay, we have negative 128 plus our next value, which is 64. Plus our next value, which is 32, plus 16, plus 8, plus 4, plus 2. And what that gives me is a 126, right? So we have a negative 128 here, and we have on 1, 2, 3, 4, 5, all 6 of these LEDs. When we add those together, we get 126. Negative 128 plus 126 will give us negative 2. So we'll have the correct output here as well. And that's how our arithmetic logic unit works for our bin-eater 8-bit computer. But I appreciate you guys for watching. If you enjoyed the video, if you learned something, feel free to like, comment, and subscribe. You guys have a great rest of your day.